Let's walk through the Chapter 2 test review. So number 1, the average rate of change of f of x on the interval between 1 and 3 is. And when we see this word average, okay, average rate of change, average velocity, all that's saying is find the change in position over change in time. Okay, so this average means that we want to find the slope between the endpoints, that there's no derivatives involved in this process. So we simply find the y values at the endpoints, and then we do change in y over change in x. In other words, change in position over change in time. So that means at these x values, 1 and 3, we're going to plug them each separately into the original function. So f of 1 will just be 4 minus 1, which is 3. F of 3 is simply 12 minus 9, which is 3. So our ordered pair is 1, 3, and 3, 3. So we plug them into our slope formula. So change in y over change in x. So 3 minus 3 over 3 minus 1 will give us 0 over 2. So that means our average rate of change on the closed interval from 1 to 3 will simply be 0. Okay, number 2, the instantaneous rate of change. Now, instantaneous, that means we want to find the exact slope, the exact rate of change at that point in time. So this requires derivatives, especially if our function is a curve. And here we have a quadratic function. There's going to be a smooth curve, and the slope is going to be ever changing. So we need to find the derivative and evaluate the derivative at these x values separately to find the exact slope at those points. So first we find the derivative. So 4x becomes 4, x squared becomes 2x, and we can simply plug the endpoints separately into the derivative function. So f prime of 1 is simply 4 minus 2, which is 2. F prime of 3 is 4 minus 6, which is negative 2. So that means the slope at 1, the steepness, the exact steepness of the curve at x equals 1 will be a slope of 2. The exact steepness of the curve at x equals 3 will have a slope of negative 2. Okay. Number 3, find d2y over dx2 for y is equal to square root of x squared plus 1. Now this notation is simply asking you to find the second derivative. So we need to go through and find the first derivative before we can get to the second derivative. So first derivative, first thing we do before we find the derivative is let's get this set up. So let's get the radical, convert the radical to be in terms of a rational exponent. And here you see that we have parentheses with terms on the inside with an exponent on the outside. So what that means is when we find the derivative, there's an inside function and there's also an outside function, meaning that we have to go through chain rule. So chain rule says we take care of the outer function's derivative first, and then we multiply by the inner function's derivative. So the outer function is parentheses to the 1/2. So the derivative of parentheses to the 1/2 is simply 1/2 parentheses to the negative 1/2. Right? We just treat the parentheses like we would as a variable. So imagine this is just it's just x. So the derivative for x to the 1/2 is just 1/2 x to the negative 1/2. Okay, but what we do is we leave the inside function untouched, and this is still we haven't gotten to the inside function derivative yet, so we leave that alone. So outside function derivative 1/2 parentheses to the negative 1/2. Now we have to multiply by the inner function's derivative, with this being a composite function. So the derivative for x squared plus 1 will simply be 2x. So that's times 2x here. And then we clean this up a bit. The 2's cancel out. The x squared plus 1 goes down to the denominator. So we have x over root x squared plus 1. Okay, so here's our first derivative. Now to find the second derivative, we have to go through the process again. I'm going to treat this using quotient rule, but you could cancel out the 2's and simply use product rule if you'd like. But quotient rule things will be a little bit cleaner with quotient rule. So with quotient rule, we have to see that to find the second derivative, we have a numerator and a denominator portion. But then this square root of x squared plus 1 will require the chain rule as well. So we have both quotient rule and chain rule. And the way that we decide which one is applied first is we look to see which rule affects the entire function. So in this case, the x over square root of x squared plus 1, this is going to be affected by the quotient rule first. And then within the quotient rule, the chain rule is only the denominator, so it'll only be a portion of within the quotient rule. Okay, so we go through quotient rule. Quotient rule says f prime g minus f g prime. So here is my derivative written out as rational exponents. So f prime g, so x becomes 1. The g function remains the same. Okay, so f prime g minus f, that's x, times g prime. So g prime is the derivative of this entire denominator, which requires chain rule because we have a composite function. Parentheses to the 1/2 is the outside function. X squared plus 1 is the inside function. So now we have f prime g minus f times g prime. So we have to find the derivative of this x squared plus 1 to the 1/2. So we bring down the 1/2, keep the parentheses, subtract 1 from the exponent, and then multiply by the inner function's derivative. So again, x squared plus 1's derivative becomes 2x plus 0, or just 2x. Remember, the constant goes to 0. All right, so now we can try, and then that's only the top portion. With chain rule, we also have denominator squared. So if we take x squared plus 1 to the 1/2 and we square that, the 2 and the 1/2 will cancel out, leaving us with just x squared plus 1. So think of it this way. If I'm squaring the square root of x squared plus 1, the square root and the square will cancel out, leaving me with just x squared plus 1. Okay, so all this is applying the quotient rule, and then within the quotient rule, there's the small portion that requires chain rule. So if we clean this up a bit, the 2's can cancel out. We can bring this x squared plus 1 to the 1/2 in the denominator of this numerator space. Hey, we can't just take this x squared plus 1 to the 1/2 and move it down to the denominator because this term is attached to this minus. So we can't just move it down. So we have to have a complex fraction here. But now with this complex fraction, we want to clean this up a bit. So we want to find a way to get rid of the square root of x squared plus 1. So I'm going to multiply the numerator and denominator by this denominator that's causing this complex fraction to occur. So I'm going to take this denominator, this square root of x squared plus 1, and I'm going to distribute this through to each term. So when I multiply these two terms together, the square roots will go away, leaving me with just x squared plus 1. And then when I distribute this through to this fraction, the numerator and denominator will cancel out, leaving me with just x squared, and that's over here. Okay. And then we have x squared plus 1 to the first power times x squared plus 1 to the 1/2. And if I'm multiplying bases, I just add exponents. So this is to the first power, this is to the 1/2. So 1 plus 1/2 gives me 3/2. Okay. Clean this up slightly more. The x squared minus x squared will cancel out, leaving me with just 1 over x squared plus 1 to the 3/2. So answer choice A. Okay, number 4, if the line tangent to the graph of the function at point 1,7 passes through the point -2, -2, then f prime of 1 is equal to. So it may help to graph this to kind of see maybe if we can sketch out a scenario for this problem. So we have a tangent line to the curve at 1 is going to be that tangent line is also going to go through these points, 1, 7, and -2, -2. Okay, so what I did was I plotted those points. Here's 1, 7. Here's -2, -2. And I'm going to just draw a curve so that that curve is going to have that same tangent as that tangent line through the point 1, 7. So so here's my tangent line. So this tangent line is tangent to this curve at 1, 7, and we know that if we can find the slope of this tangent line, then we have in effect found the slope of the curve at that point as well, because they're telling us that this tangent line, this is the tangent line for this graph. So if I find the slope of this tangent line, then I found the slope of the curve at that point as well. So I'm given 2 points of for my tangent line. So if I just find the slope of that tangent line, then I have the slope of that curve. So to find the slope of the tangent line, we simply do change in y over change in x, and that'll give us -9 over -3, which is +3. So the slope of the tangent line to the curve at x equals 1 will be slope of 3. All right, number 5. Find a and b such that ax cubed exists for x to the left of 3, and x squared plus b exists for the graph for the portion where x is greater than 3. And we know that this piecewise function is differentiable everywhere. So now we have 2 branches of the graph, or 2 portions, piecewise functions, and they say that it's differentiable. So what that means is that these 2 branches are going to connect at x equals 3. So if they connect at x equals 3, then this word differentiable means that it's a smooth curve. So it's if it's a smooth curve, then we know 2 things about the graph. First, we know that the graph is continuous. We know that these 2 graphs will meet at x equals 3 with the same y value. Okay, these 2 graphs will meet at the same ordered pair. So at x equals 3, these will have the same y value. So not only that, but differentiable also means that it's a smooth curve. So the graph is connected at x equals 3, and the graph is smooth at x equals 3. Okay, so what that also means is that at x equals 3, they're going to share the same y value, and also at x equals 3, they're going to share the same slope. Okay, so what that means to set up the problem is we're going to set the piecewise functions equal to each other, okay, to take care of this this continuity property here. So we know they're going to share the same y value, so we can simply set these 2 functions equal to each other at x equals 3, and we know that they must match. Okay, differentiable means that it's a smooth curve, that their derivatives will be the same. They're going to have the same slope, so we can find their derivatives, set them equal to each other at x equals 3, and at x equals 3 they must share the same slope. Right. So now we have 2 equations that we can set up, systems of equations, most likely using substitution to plug in to the other and solve. Okay, so we're going to take the continuity portion first. We're going to set the left graph equal to the right graph, and we know that they must connect at x equals 3, so we can simply replace x with 3. So a times 3 cubed is equal to 3 squared plus b. 27a is equal to 9 plus b. So right now that's as far as we can go. Okay, we can't solve for a, we can't solve for b yet, because we have just we don't have this in terms of one variable yet. Okay, so the way that we get this into one variable, we're going to use this other equation that we know. And the other equation is that we know that the 2 functions are differentiable, meaning that we can set their derivatives equal to each other. So let's find the derivative for ax cubed. A is just a coefficient, so the derivative for x cubed is simply 3x squared. So we just write 3ax squared. Okay, the derivative for x squared is 2x, and the derivative for b, which is a constant, is going to be 0. So x squared plus b turns into 2x. So we have 3ax squared equals 2x. We found the derivatives. We set them equal to each other. And now we know that they must have the same slope at x equals 3, so I can replace 3 in for x. So I get 3 times 9a, which is 27a. So 27a is equal to 6. Okay. And now if I solve for a, I get a is equal to 6 over 27, which reduces to be 2 over 9. Okay. So now I have a solved. So now I can plug this into the first equation I found. So plug 2/9 in for a. So 27 times 2/9 is equal to 9 plus b. 27 divided by 9 is 3. 3 times 2 is 6. 6 equals 9 plus b. So if we solve for b, b will just be 6 minus 9, which is -3.